This tutorial will teach you how to program analog-style synthesizers. It explains all about oscillators, envelope generators, filters, and LFOs. These are the basic building blocks used to create all analog synth sounds. Modern synthesizers are very sophisticated, and most come with tons of great presets. Sadly, many musicians never venture beyond these presets and don't bother to learn what all those knobs and switches really do. But learning how to make your own patches is very rewarding and a lot of fun. To truly understand how analog synthesizers work, it's useful to view the waveforms on an oscilloscope. This way you can see what's going on under the hood. Ironically, for these examples of programming analog synthesizers, I'll use the fabulous DreamStation software synthesizer you hear playing. The DreamStation is similar to a Mini Moog, but since it's software there's no hiss, it has less unwanted distortion, and doesn't drift out of tune. The music you're hearing now was done entirely with the DreamStation synthesizer. Even though we'll use the DreamStation synthesizer for these examples, the basic principles apply to all analog synths. When I was learning about analog synthesizers in the 1970s, the Mini Moog and ARP 2600 were popular, but very expensive for a poor musician like me. With the help of my friend Leo Taylor, I learned how to design and build my own analog synthesizers. Leo and I designed several analog synth prototypes over the course of several years, and the one you see here is the final and most sophisticated model we made. I still have this monster in my basement, though I haven't fired it up in years. That's my synth playing the melody in this disco version of Over the Rainbow I recorded back in the 1970s. When this lesson is done, you'll understand the relation between what you're hearing and what's shown on the oscilloscope. You'll also understand what all the knobs do and how to adjust them to create the classic analog synth sounds we all know and love. Early analog synthesizers used physical patch cords to connect the various oscillators, ADSR envelope generators, and filters together. Even though patch cords are rarely used today, the term patch is still used to describe a group of modules, their knob settings, and how they're connected. When the Mini Moog was first introduced, one of its coolest features was having all of the components permanently connected in musically useful ways. This made it much easier and faster to create sounds, and avoided crackles and dropouts from dirty patch contacts. Likewise, DreamStation is set up with the oscillators permanently connected to the ADSR amplifier, which then goes to the filter, and so forth. Oscillators are the heart of every analog synthesizer, and they create the sounds you hear. An oscillator in a synthesizer is the electronic equivalent of strings on a guitar or piano. But where a string vibrates the air to create sound, an oscillator varies a voltage, which eventually goes to a loudspeaker. Either way, the end result is sound vibration in the air you can hear. There are 5 basic waveforms used by most synthesizers: sine, triangle, sawtooth, square, and pulse. Since these waves eventually go to a loudspeaker, their shape shows how the loudspeaker will move. That is, when you play a sine or triangle wave, the speaker cone goes forward smoothly, then backward smoothly. But a square wave or pulse wave causes the speaker to jump quickly from one position to another. Note that the fast movement at the wave's edge is what creates the harmonic overtones. In techno speak, this is called the wave's rise time. The steeper the wave transition, and the faster the speaker moves in turn, the more high-frequency content there is. All static waveforms contain one or more frequencies. The simplest wave type is a sine wave, which contains only one frequency, a fundamental pitch. Without any harmonics to add character, the sound is pretty boring. We can vary the volume over time, but it's still not very interesting. A triangle wave has only odd harmonics, so an A220 note contains the 220 Hz fundamental, the third harmonic at 660 Hz, 1100 Hz as the fifth harmonic, the seventh harmonic at 1540 Hz, and so forth. A square wave also has only odd harmonics, but the harmonics are more prominent than in a triangle wave, so the sound is brighter. We can modify a square wave to add even harmonics by varying what's called the duty cycle, or pulse width. When a square wave is asymmetrical, it's called a pulse wave, and the lack of symmetry creates the even harmonics. DreamStation also has a control to modulate the pulse width over time. Notice how the sound becomes nicely animated. Another type of wave, the sawtooth, also contains both odd and even harmonics. Like the pulse wave, the sawtooth is also asymmetrical. Note there are some minor artifacts in these waveforms, mostly rounding at the corners and a touch of ringing on the sawtooth and square wave sharp edges. It can be difficult to generate a textbook perfect waveform, and it's no easier with a hardware analog synthesizer. If you look at the waveform of most hardware analog synths, you'll probably see similar artifacts. Most analog synthesizers use what is called subtractive synthesis. This type of synthesizer starts with a complex wave having many harmonics and uses a filter to selectively remove the harmonics to get different tone colors. The other type of analog synthesizer uses additive synthesis. In this case, many individual sine waves are added together in varying amounts to create the harmonics. A Hammond drawbar organ is a perfect example of additive synthesis. Here, each drawbar controls the volume of one frequency, so you construct the desired timbre manually. There are software versions of drawbar organs, and the native Instruments B4, shown here, is a perfect example. I love the native B4, and I've used it in many of my pop tunes. However, this tutorial will focus on subtractive synthesis, since that offers more options and is what we usually think of when talking about analog synthesizers. Earlier I mentioned that having harmonics makes a sound more interesting, as does varying the volume over time. With analog synthesizers, making the sounds more interesting is the name of the game, and varying the sound over time is a great way to add interest. For example, a good oboe player will vary the tone color in vibrato as a note sustains. Or a cellist may slide gracefully from one note to another once in a while. These musical qualities, and many others, are desirable with synthesizers too. Another way to add interest is to use two or more oscillators in unison, but slightly out of tune with each other. This is not unlike the difference between a solo violin and a violin section in an orchestra. No two violin players can be perfectly in tune, and the very slight differences in pitch and timing enhance the sound. Let's hear what that sounds like. One way to add interest is to vary the sound over time. The simplest parameter to adjust is volume. This is handled by the ADSR. The ADSR is an envelope generator, which is a fancy way of saying it adjusts the volume over time. ADSR stands for attack, decay, sustain, and release. Some synthesizers have additional parameters, such as an initial delay before the ADSR sequence begins. Note that the attack, decay, and release parameters control the length of each event, but the sustain knob controls the sustained volume level. Let's take a closer look. The attack time controls how long it takes for the volume to initially fade up. Once the volume has reached maximum, it then decays at a rate set by the decay control. But rather than always decay back to zero volume, it instead fades to the sustain volume level. This lets you create a short note burst for articulation, then settle to a lower volume for the duration of the note, Only after you release the key on the keyboard does the volume go back to 0 at a rate determined by the release setting. Now let's watch the ADSR at work on the oscilloscope. The ADSR times are relatively slow compared to note frequencies, so the oscilloscope sweep time is also set slow, so you can see how the ADSR changes the volume over the course of several seconds. When I take my hand off the keyboard, the note then fades out according to the release time setting. The ADSR lets you create very short staccato notes, as used in the hit Popcorn from 1972. The attack is very fast, and the decay is almost as fast. In this case, the note should not sustain, so the sustain level is set to 0. By extending the decay time, notes sound like a guitar, then more like a piano. The sustain level is still at 0. Bringing up the sustain level adds a punchy quality to the sound where it jumps out briefly, then settles into the lower volume for the rest of the note's duration. We already saw how an ADSR controls volume over time, and an ADSR can also control the filter to vary a note's timbre over time. When the filter is used with an ADSR to change the tone quality, the amplifier ADSR can be used too, or it can be disabled. Many synth sounds use the filter to sweep the frequency either up or down only, though you can of course have it sweep both ways. In truth, the ADSR always sweeps the filter both up and down, but one direction is so fast that you don't hear it. Many synth patches use one of two basic ADSR filter settings, where the attack is short with a longer decay, or vice versa. The filter's cutoff knob sets its initial frequency. The filter's ADSR then sweeps the frequency up from there, and back down, over time depending on the ADSR settings. For clarity, I'll use the Sonitus equalizer to show how a synth filter's frequency response changes. This equalizer shows its frequency response as a graph so you can see how it changes. I'll switch back to the DreamStation synthesizer in a moment. A low-pass filter allows only low frequencies to get through, so you may prefer to think of it as a high-cut filter. When opened fully, all frequencies pass through, and as the frequency knob is lowered, it filters out high frequencies starting lower and lower. Here's the filter sweeping up and down. Now here's the same type of sound as played by the DreamStation synth. The DreamStation filter you just heard is a low pass with a slope of 24 dB per octave. 24 dB per octave is a very steep slope, which rolls off higher frequencies severely. This is the classic filter type used most often in analog synthesizers. The DreamStation synthesizer also has a few other filter types. Filter type Low Pass 2 we just heard has a steep slope of 24 dB per octave. This means that for each musical octave above the cutoff frequency, the level is reduced by 24 dB, which is a substantial reduction. Filter type Low Pass 1 is similar, but the highs roll off at only 12 dB per octave. Since the highs are reduced less, this filter setting yields a slightly brighter sound. There's also a high-pass filter type that leaves the highs intact and progressively reduces lower frequencies. The bandpass filter type is used in wah-wah pedals. The Formant filter has 4 separate bandpass sections, and this type of filter emulates the multiple resonances in your mouth. When you sing a note, your vocal cords vibrate at the note's pitch, but your mouth has several different resonating cavity areas. As you voice different vowels to create the sounds A, E, I, O, U, you're changing the size and shape of those cavities in your mouth. This in turn emphasizes different harmonics in the wave created by your vocal cords. The Formant filter works in a similar fashion to impart a human voice quality. Another important filter parameter is resonance, which is more easily shown with the Sonatus EQ screen. When the resonance is increased on a low-pass filter, a narrow resonant peak forms at the cutoff frequency. This emphasizes that frequency and brings out single harmonics one at a time as it sweeps up or down. You can see on the oscilloscope how the sawtooth wave starts with all harmonics filtered out. Then, as the filter sweeps higher, each harmonic is emphasized in turn. That's why you see smaller sine waves riding on top of the fundamental pitch. As the filter sweeps higher, you see the secondary frequency change as each harmonic is boosted one by one. As with an ADSR to control the volume, you can do the same with a filter to make short staccato notes or long sustained tones. With a filter, the sweep direction changes the basic character of the sound. The filter's gain control determines the width of the sweep range. The last filter parameter we'll consider is keyboard tracking. Normally, the filter is swept automatically for each note by its own ADSR or left at a static position. Most analog synths also have an option for the filter to track the keyboard, so playing higher notes moves the filter frequency higher in addition to any sweeping effect. For example, if you have a resonant filter boost that brings out the third harmonic of a note, you'll want the filter to track those notes as you play up and down the keyboard. Keyboard tracking also makes possible sound effects, such as wind noise that can be varied in pitch or even played as a melody. We'll wrap up our tutorial by looking at a few remaining odds and ends. All analog synthesizers include an LFO to vary the note pitch, the volume, or the filter frequency. LFO stands for Low Frequency Oscillator, meaning the frequencies are too low to hear as musical pitches. Rather, they vary the sound of the oscillators that do create the musical notes. An LFO creates a tremolo effect when used to modulate the volume, or a vibrato effect when varying the pitch, or a wah-type effect when used with the filter. The DreamStation LFO uses buttons to route its output to the various other components. In this case, the destination, marked DEST, on the screen can be sent to Oscillator 1, Oscillator 2, the pulse width setting for Oscillator 1, or the filter's frequency. The LFO also offers 4 different wave shapes. Note the noise wave shape, which is basically a random value that keeps changing. This is great for varying the frequency of a formant filter to create talking robot voices. Vibrato is similar to using the LFO to vary the note pitch, but it offers only a sine wave shape. Besides the rate and depth control, there's also an initial delay that tells how long the note should play before the vibrato begins. This is similar to the way a violinist might play a note, rather than applying full vibrato to each note the moment it starts. Portamento is another common synthesizer effect, and it has the effect of smoothly sliding the pitch from one note to another, rather than jumping quickly. In this case, the portamento knob controls how quickly or slowly the sweeping happens. If you want to make a synth sound more like an electric guitar, distortion is just the ticket. Distortion in DreamStation clips the tops off the notes, just as a guitar amp does when overdriven. Here you can see that as the distortion is increased, the tops of the sine wave are flattened. This is what happens when you overdrive an amplifier. In this tutorial, we looked at the basic building blocks of analog synthesizers, including oscillators and waveforms, the ADSR, filter types, LFOs and vibrato, and portamento. We also saw the waves visually on an oscilloscope to better relate what we hear with what is actually happening. All of the basic parameters shown in this tutorial can be applied to other synthesizers, whether hardware or software. Thanks for watching.